Hey guys, welcome back. Just figured we'd go ahead and do a quick uh, video about electromagnetic induction. This is our 25th video in the series, and we're just going to keep chugging along. We've been talking about electrostatics and magnetism, and we've been kind of implying that the two are very closely related to one another. Matter of fact, we use the word electromagnetic all the time when talking about waves or phenomenon. Now we're going to talk about electromagnetic induction. Electromagnetic induction kind of implies that the two are kind of manifestations of the same thing, and in fact they are. We talked about magnetism and magnetic force last time. Let's jump into this right away. Okay, here's an apparatus that's actually used for electromagnetic induction, but because we don't know what that is yet, we can't really describe it. There's not going to be a lot of photographs in this slideshow or in this video. There'll be a few, but much of it is just conceptual. So if you've already gone through previous lectures on electrostatics through magnetic force, you'll kind of get the idea of what's going on as we go through. So electromagnetic induction was discovered by a guy by the name of Faraday and another partner of his by the last name of Henry. And what they discovered was that you can induce a voltage by simply changing the magnetic field strength in a coil of wire. So imagine in this image down here, we have a hand that has got a magnet. Here's the north, this would therefore be the south. And basically it's being inserted into this coil of wire. And as it's being moved into the coil of water, it generates a voltage, right? So it turns out that the inducement of voltage can be done through increasing the number of loops in a wire in a coil. So it turned out that the more loops that were here, the greater the voltage. If you remember our discussion on magnetic force in a previous video, the number of loops is actually very important. And in electromagnetic induction, it's also quite important. Increasing the speed of the magnet entering and leaving the coil. So we also talked about the fact that when things move, it's the manner in which they move also has an important role to play in electromagnetics. As I said before, make sure that you have seen those previous videos. You'll understand what I mean by this. Slow motion produces hardly any voltage. You barely put it in. But rapid motion produces much greater voltage. All right, and this is a nice image of Professor Faraday, whose lab is still preserved for us to go and visit if you were ever to go to England. So voltage is induced in the wire loop whether the magnetic field moves past the wire or the wire moves through the magnetic field. In other words, it doesn't really matter if I take the magnet and I put it over the wire or if I put the wire around the magnet. As long as there's relative motion between the two of them, I get a voltage, right? And that's what this is indicating right here. When you take a magnet and you plunge it into a coil with twice as many loops as another, twice as much voltage is also induced. So here we see we plunge this magnet in there, we read the voltage, but twice as many loops or even more than that, and the voltage actually increases commensurately. If the magnet is plunged into a coil with 3 times as many loops, 3 times as much voltage is produced. So you get the idea. It's proportionate. The actual voltage number, the mathematics can be a little complicated, but you get the idea. It triples if you triple the number of loops, all other things being equal. All right. You're not going to, by the way, as we're going through this, you're not going to see a lot of equations, just like you didn't see a lot of equations on magnetic force. They're a little sophisticated, require some knowledge of calculus or at a minimum trigonometry. But that doesn't make it necessarily hard. And many of the concepts can actually be learned through a basic physics textbook. But with that said, I don't want to get too much into the math. The idea is to stay conceptual in these ideas. So Faraday's law brings about some interesting observations that we can work with or standards that we know that we can expect. So Faraday's law states that an induced voltage in a coil is proportional to the number of loops multiplied by the rate at which those magnetic field changes within, multiplied by the rate at which the magnetic field changes within those loops. So if it's going fast or slow, you multiply the rate of change times the number of loops, and it's proportionality. The amount of current produced by electromagnetic induction is independent on, is dependent, I inadvertently said independent, dependent on resistance of the coil, circuit that it connects, and the induced voltage, right? So this is related strongly to Ohm's law, right? Ohm's law is resistance. The circuit that it connects, right, again, includes the resistance and the voltage and the induced voltage. All of these things are related. So again, previous lecture talks about Ohm's law. It is more difficult to push the magnet into a coil with many loops because the magnetic field of each current loop resists the motion of the magnet. So having a single loop is very easy to put a magnet through, but if you have a whole bunch of them, you try pushing down in it, it's extremely difficult. You actually produce a force that resists the movement of that magnet. But where's that going? That implies that something's happening. So, and of course it has to do with the voltage. So voltage induced in a wire requires changing magnetic field in the loop by moving the loop near a magnet, moving a magnet near a loop, or changing the current in a nearby loop. This is important. And this is used in activation of traffic lights by car moving over underground coils of wire. So you guys might have seen this at stop signs, right? And basically what happens is your engine, which is a large conductor, would sit right above this. You know, you pull up to the stoplight, your engine is spinning above it, and what that spinning is doing, it's basically a moving conductor, and that moving conductor is inducing a magnetic field. And that magnetic field is then interfering with this wire that is buried in the asphalt below your vehicle, and that produces current. It's pretty interesting. And that current then goes to the sensor that tells the light to change from green or from red to green. Triggering a security system at the airport by altering magnetic field in the coils as one walks through. You have biomagnetism. As you walk through a stall, you have the ability to actually induce a current that can be read by a computer or by a scanner. Scanning magnetic strips on the back of credit cards, right? Those work because you have to slide your card, right? It doesn't work too well if you just put the card down. The card has to be swiped, and it's the swiping of the card that allows the magnetic strip to be read. You need to have motion. It has to be a changing magnetic field. The recording of sound on tape, right? Many people don't use tape anymore, so it's really not the best example, but you get the idea. This is one of the ideas that was used in the 70s, 80s, and 90s for recording equipment. Electronic devices and computer hard drives and iPods. So basically how your hard drive works is by use of Faraday's law. So a generator is kind of the crux of how all of this stuff works, right? We've talked about how to make an electric motor, but it really works on the opposite. Again, previous video, go and learn about the electric motor. In the case of the electric motor, we actually see our magnet with our rotating loop in here. In the case of an electric wire, this was connected, in the case of a electric motor, it was connected to a battery. And what you would do is you'd plug the battery in, it would spin the loop, and that loop spinning through this magnetic field could be used to do work. For example, power a car or a bicycle or whatever. In this case, we can reverse the process. Instead of having the loop spin, we spin the loop through some physical process. And as it spins, right here, this spinning induces a current, according to Ohm's law. And we can use that to power a light. So basically, instead of draining power, we manually spin the motor, and it produces electricity an electrical output that can be measured, used, and put to work. This converts mechanical energy into electrical energy via coil motion, and it produces alternating voltage and current, AC. And that's exactly what power plants do, is they basically take coal or nuclear or whatever, you name it. And it's hydroelectric, same thing. The whole goal is to spin a coil. That's all these generators do, is spin a coil to be able to produce an electrical output that can go out onto the grid. And it's doing it at an AC, as an AC, alternating current. And here we see the loop right here as it spins around. The frequency of alternating voltage induced in a loop is equal to the frequency of the changing magnetic field within the loop, right? So as the loop spins, it has to spin. In the United States, it spins 60 hertz or 60 cycles per second. So the loop is spinning at 60 hertz. That's our goal. And that's exactly what we see in our AC current. You might want to go back and review the video dealing with AC current if this is somehow foreign to you. I believe that was our video 22 or 23. Okay, using Michael Faraday and Henry's discovery of electromagnetic induction, a great man, Nikola Tesla, and George Westinghouse, who actually in some ways revolutionized the world. The discovery of the physics by Faraday is important, but Tesla showed that it works for common people, and this was a big deal. They showed that electricity could be generated in sufficient quantities to light cities. And so basically, they started spinning a coil. That coil could be used to generate light. And they started using steam, but it doesn't have to be steam, right? We've got steam coming across a blade that spins the whole apparatus, spins a generator that's inside of a magnet, and that induces current. But we can use things like water, right? We can put water spinning down a river or coming down a river, and as it comes through, we just put a dam in the way of it, and we force the water to spin a turbine as it goes by, and that'll produce electric power. What about wind turbines, say on a wind farm? It's the exact same idea. They're just sitting there spinning an electric generator. That's all it's doing. Nuclear power plants generate steam. Coal power plants generate steam. Oil burning power plants generate steam. And that steam is used to spin these blades, right? So there's many ways to actually produce power. The main goal is to just simply spin this thing to be able to produce an electromagnetic induction, to be able to induce current in this wire, AC current in this wire. So an important aspect of understanding how electromagnetic induction kind of plays a role in our everyday life is to understand how transformers work. And I'm not talking about the toy, I'm talking about the actual electrical transforming stations that exist all over the world. A transformer is simply the ability to transfer the voltage of one current into another voltage. And the best way to do that, of course, is through alternating current. We're going to describe this here in a minute. As a matter of fact, it's only possible through AC current. So input coil of wire, the primary power by AC voltage source. So we have a wire that comes in here. It's wrapped around this this coil here. Basically, we're producing this coil, or I'm sorry, it's wrapped around an iron core, which is located right here. And it's got some voltage, it's got some current. It's following Ohm's law. We want to convert this into something else. So we're going to have an output coil of wire. That's the secondary coil to an external circuit. So here we have our external circuit. So for example, from the power plant, it might be coming in at 10,000 volts, but our light socket works at 120 volts. So we need to get that converted. So what do? Both are wound on a common iron core. So here's the primary, here's the secondary. We want to be able to get the electricity from here to that light bulb, but we've got to change the voltage. So they're both around the same iron core so that the magnetic field on the primary passes through the secondary. Cool, got it. So we've got the magnetic field. Notice that the magnetic field lines are going through both. Core is important. Uses an alternating current and voltage in one coil to induce an alternating current and voltage in a second coil. All right. So if this is going to be producing an magnetic field and it's alternating, right? Remember, the idea is that if it's moving back and forth, the charges within the wire are going to be inducing a magnetic field. But the magnetic field that is produced by the primary is also going to be alternating, right? It's going to be going back and forth, back and forth, back and forth in strength, and it's going to be changing in its dynamics. 60 cycles per second. Well, what does that do? Now we have a changing magnetic field that's going to produce a voltage in the secondary. So we're going to induce magnetism, which in turn is going to induce current into the secondary. All right. That's basically the idea of how these transformers work. And we can use this to do some really cool things. We're going to get into there a little bit of just kind of conceptual math here in the next slide, so we'll explain what that means. Transformers can be step up or step down voltage, right? You can step it up, you can go from 100 volts to 10,000 volts, or you can go from 10,000 volts and step down to 100 volts. So a step up transformer produces a greater voltage in the secondary than supplied by the primary. The secondary has more turns in coil than the primary. We'll explain what this means here in a moment. But basically, if you're going to step up, you need more coils. So you go from fewer coils to more coils. If you're going to step down, you produce a smaller voltage of the secondary than supplied by the primary. So the secondary has less turns in coil than the primary. So if you want to go from a lot of voltage, say 10,000 volts, to 110 or 120 volts in your house, you're going to use a lot less coils to do that. And that's, by the way, if you've ever seen power lines, these are transformers. This is where this happens, right? You might have 10,000 volts here, but what's coming out of it and maybe being fed to your house is only about 110 or 220. 220 is pretty normal too. And so the proportionality is pretty straightforward. You take the primary voltage, say 10,000, and there's some number of primary turns that go along with that that's associated in the transformer. If we want to get the secondary voltage to 110, so let's keep it simple. Let's go from 10,000 to 100. That means that the voltage here is 100 times larger. To be able to get that, the number of secondary turns needs to be 100 times smaller than it is over here. It's just a proportionality argument, right? So the transformer transfers energy from one coil to another. That's really all it's doing. It's simply transferring the energy. It's just doing, what it's really doing is it's not only just transferring the energy, it's converting the voltage. Power into the primary equals the power into the secondary. It doesn't change, it's still the same. So if you take the voltage times the current in the primary, it's going to equal the voltage times the current in the secondary. So an example, voltage stepped up before leaving the power station. The voltage is stepped down for distribution near cities by cables that feed power to the grid. So as these high voltage cables go across an entire landscape, once they get near their destination, they get stepped down to 220 or whatever it is locally, because it doesn't necessarily need to be that efficient. It's very close to being to its destination. Voltage step down again before being supplied to businesses and consumers through substations, right? So at that point, it might go from 10,000 to 220 or 10,000 to 1,000 and then down to 220 or 120. Pretty normal process. The idea is to simply constantly step it down to the point where it gets where you can use it in your house. Self-induction also happens, and you have to be really careful when you're doing this. Some people don't expect it to happen. This happens with a lot of old TVs. We've also seen this with capacitors. This is one of the cases where you have to be really careful. Current carrying loops in a coil interact not only with loops of other coils, but also with the loops of the same coil. So as the current is basically going through, they're interacting with each other. That's really important. So each loop in a coil interacts with the magnetic field around the current and other loops of the same coil. This is self-induction, right? So the problem is not only is the circuit producing or the induction on things around it, it's inducing itself. And when the switch is opened, so in this case, this girl here is opening the switch, the magnetic field of the coil collapses, all right? Because what have you done to the current? It stopped it. However, remember, to be able to induce a current, you need a changing magnetic field. And when you go from full magnetic field to no magnetic field, that's a huge change. That also means that whenever we have all these major changes, we're going to get a huge voltage. We're going to actually get current. And so this sudden change in the field, even though it's a collapse in the magnetic field, can induce a huge voltage, and you can shock yourself pretty badly. You have to be careful with self-induction. This is a common problem. Okay, so how does power get transmitted? I've kind of been hinting about it. I've been kind of throwing numbers out there. But let's go ahead and put some solid numbers to it. Almost all electrical power or energy sold today is in the form of AC because of the ease with which it can be transferred from one voltage to another, right? If you don't have AC, transformers don't work. You need changing currents. Changing currents produce magnetic fields, but they also produce changing magnetic fields. Those changing magnetic fields can then be used to step up or step down through coils on a secondary. Large currents and wires produce heat and energy losses, so power is transmitted great distances at high voltages and low currents. You don't want a lot of current moving around. It's a lot of, remember we're talking about the resistance, right? The more you're moving actual electrons, the more likelihood you're going to deal with large amounts of resistance. So it's better to transmit high voltage. Power is generated at 25,000 volts or less and is stepped up near the power station to as much as, wow, check this out, 750,000 volts for long distance transmission. That is a huge step up. It is then stepped down in stages at substations and distribution points to the voltages needed in industrial applications, often 440 volts or more, and for the home, 240 and 120. So you have all kinds of different apparatuses that are playing roles as you're going through this. But you need to have transformers that step up and step down the voltages, because you can use that to make your power grid much more efficient. And remember, AC current allows for all of this stuff to happen. You cannot get this with DC. So electromagnetic induction is a two-way street. And we've been kind of going back and forth on this. Faraday's law simply states that an electric field is induced in a region of space in which a magnetic field is changing with time. Right? So if you have a changing magnetic field, you're going to get an electric field. Maxwell later on came in and said, yeah, well, it goes both ways, it turns out. So if you have a magnetic field that, or states that a magnetic field is induced in any region of space in which an electric field is changing with time. So if you're changing one, you're inducing the other. And if you're changing a magnetic field, you're making an electric field. If you're changing the electric field, you're going to make a magnetic field. And Maxwell actually put some really good and useful equations to this. Like I said, I regret that we won't be covering them in this class, but good stuff. It's really, really interesting. So this is going to be our final slide in our little presentation here. Like I said, sorry that we don't have a lot of beautiful images here, but a lot of this is conceptual. So field induction, turns out, is the basis for light. Light is produced by the mutual induction of electric and magnetic fields. So in open space, and we're going to do a whole video on light, as a matter of fact, it's the next video in the series, it talks about the relationship that exists between electric and magnetic fields to produce light. Not really, they're shades of the same thing. The speed of light is the speed of emanation of these fields. So as electric fields are extended out into space and magnetic fields are extended into space, the rate at which these fields are emanated, or the influence of which they have into deep space and affect matter all around you, is the speed of light. So if it's too slow, the regenerating fields die out, it turns out. If it's too fast, the fields build up to a crescendo, or in a crescendo of ever-increasing energy. We're not going to get into why they believe this. This is a little more sophisticated of an argument. But basically the same. You go too slow, fields won't work. You go too fast, you have too much energy. But if you go right at the speed of light, the speed of light that we see everywhere, it turns out it's just right. And you get the propagation of electric and magnetic fields in all directions. They move at exactly the same speed. And we recognize this as the electromagnetic spectrum, which includes visible light that we can see with our eyes. All right, so with that said, there's a lot of really interesting stuff going on with electrostatics, magnetic fields, magnetic forces, but it turns out, there really are different sides of the same coin. And by the time we get to special relativity, you'll actually understand that very clearly, and it might actually change your perspective on the fabric of the universe, and kind of might even have some existential questions when you're done with the class. So anyways, with that said, if you have any questions or comments, meet me on the discussion boards or send me an email. Until next time, I hope you have a good one. Bye.